So my name is Fardosa, and I'll be doing a presentation on my milestone 4 for deep learning applications. In this video, I'll be walking through the coursework project where I built a deep learning model to classify brain tumors using MRI images. I'll explain how the data is prepared, how the model is built, and how well it performs. All this will be in step by step. So let's start with the key Python libraries. I use NumPy for numerical operations and managing arrays, OpenCV to load and read images files from disk, PIL to resize and format images correctly, TensorFlow and Keras, the deep learning frameworks I use to build and train the model, Matplotlib and Seaborn to plot training results and visualize performance metrics, scikit-learn for splitting the dataset, evaluating the model, and computing class weights, and finally, image data generator from Keras, which I used to augment the dataset and prevent overfitting. Next step, I downloaded the dataset from Kaggle. As you can see, there's the path to dataset files. Next, I loaded the classes. So here we have 4 classes of the brain tumor types, and the image will be resized to 128 for the pre-processing. Every image needs to be cleaned and standardized before it can be used by the model. I created a function that does the following. So here you can see the function. It loads an image using OpenCV. It checks whether the image is readable. If not, it prints out a warning. Since OpenCV loads images in BGR format and most models expect RGB, I converted the color space. I then resized the image to 128 by 128 pixels to ensure consistency. Finally, I normalized the pixel values by dividing them by 255, scaling them from 0.0 to 1.0. This makes training more stable and efficient. In the next step, I load the dataset. So to load the dataset, I loop through the root folder that contains subfolders for each class, the 4 classes. For each image, I applied the pre-processing function. I stored the image in a dataset list and its labels as a number based on its class. Once done, I converted the labels to one-hot encoded format using Keras utilities. This is ideal for multi-class classification. Next, I calculated the class weight and also showed the class distribution. As you can see here, we have 4 classes: glioma, meningioma, no tumor, and pituitary. Each class has well over 1,000 images, which shows that this is a well-balanced class. No tumor has the most images. Other than that, this is a well-balanced for the deep learning model CNN. Next, I visualize the sample images. Here you can see 6 images from different classes, just to show you how the MRI scans look like. The next step, I performed data augmentation. So here I applied rotation, horizontal flip, and zoom range. As for the vertical flip, I did not apply it as it's not appropriate for medical images. And next, I fitted the the training set into the into the data gen. Next, I defined the convolutional neural network. Here's how I built my CNN. I started with a convolutional 2D layer with 32 filters and ReLU activation, followed by max pooling. Then I stacked another convolutional 2D layer with 64 filters, again followed by pooling. I deepened the model with 2 more convolutional 2D layers with both 128 filters, each followed by a max pooling layer. I flattened the output and fed it into a dense layer with 128 neurons using ReLU. To reduce overfitting, I applied a dropout layer with a 50% drop rate. This drops randomly 50% of the neurons during the training. Finally, I used a dense output layer with 4 neurons, 1 for each class, and a softmax activation to generate class probabilities. Once I was done with the model, I compiled the model using categorical cross entropy as the loss function, Adam as the optimizer, and accuracy for my evaluation metric. As for the categorical cross entropy, this allows me to calculate how far off the prediction is from the actual prediction. Adam as the optimizer was also used, and for the accuracy, for the evaluation matrix, I used accuracy. Next step, I trained the model using the fit method. To improve generalization, I used image data generated to apply data augmentation, like the random rotation, flips, and zooms. I also trained the model over 20 epochs with a batch size of 64, and also used validation set to monitor performance and prevent overfitting. Here you can see the model accuracy and model loss over all the epochs. This you can see there's a steady increase in the model accuracy for the training accuracy and validation accuracy. And there's also a steady loss in the train loss and validation loss across the epochs. Here I plotted a confusion matrix to show the true labels against the predicted labels. And then finally, I added a classification report. So after training, I evaluated the model on a separate test set. Here's the summary of the classification report. Glioma had high precisions but lower recall, which means it rarely mislabeled other classes as glioma, but it missed a few true glioma cases. Meningioma was the weakest class. No tumor had almost a perfect recall. Pituitary performed also well, just like no tumor. Overall, the model achieved a 91% accuracy on the test set. Next, I saved the model I used the model.save to save the model. I named it braintumor.h5, which will be used in my web app. So as part of this coursework, I also built a simple web app where users can upload an MRI scan and the model will predict whether it shows signs of glioma, meningioma, pituitary tumor, or no tumor at all. It's designed to demonstrate how AI models like this one can eventually support clinical workflows, not to replace doctors, but to assist with faster, more consistent decision making. I used a simple HTML and CSS from Bootstrap to style my web app. And after that, I allowed the web app to accept the image, pre-process it, and predict it according to its correct class. I've already run this cell, so I can go ahead and click on the URL. So this is a public URL. If you're using Collab, you can click on this link. And if you're using Jupyter Notebook, this link should work. So I'm going to go ahead and use this one. So this is how my simple brain tumor classifier looks like. It has a section where you can choose the file and then upload and predict. Here it will upload the image into a directory, and then from there it will predict it according to its correct class. So I will upload an image. So here I have an MRI dataset, which consists of training and testing. So this testing dataset is an unseen dataset, which will be suitable for testing out my web app. So here I will try and choose a class, and then from there I will try to predict the class. So this is pituitary. We'll just select any random image and then upload and predict. So here you can see that the prediction results came back. The type of tumor is pituitary, which is correct. So we can also upload another image again. Let's use a different class, no tumor. Here you can see that it also predicted this as a no tumor class type. You can choose a different so this is meningioma. Yes, and there it has predicted it as meningioma with a 0.775 confidence. Thank you so much. This is my final coursework for milestone, and this has been Fadosa signing out. Thank you.